Hey ChemExcel, this video is about the nature of the reactants and the effect that they have on rate of reaction. We're going to look at the two things that you can focus on when analyzing the nature of the reactants and how to determine if those things are indicating a faster or slower reaction. So the first thing to focus on is molecular complexity. You get a good feel for this when you just look at the formula. The formula is very small, doesn't have a lot in it, right? Versus if the formula itself is much larger and shows a lot more atoms. Small and simple molecules, especially those that are symmetrical as well, are going to be easier to react with. The reason for that is there's going to be a lot more opportunities for the collisions to have proper orientation, right? When you're looking at a molecule as symmetrical, it matters less sort of which side you actually hit the molecule from. You have a lot more opportunities to have the exact same effect, whether you're on the right or the left or the top or the bottom or the front or the back. It's more likely to work because of the symmetry. When you have bigger molecules, complex molecules, and asymmetrical molecules, they're going to be harder to react with. You have to collide in the exact right spot, and so most of the collisions aren't going to be effective just from an orientation perspective. All right, over here we got ethanol molecule, looks like a dog. Kind of figured everyone needed that right now, so threw that in there. It's a little bit more complex than the symmetrical methane molecule that we see up here. All right, if you need to break off the OH group here, can see that that's not going to work if you're hitting the molecule somewhere on the other side. Okay. We've got some type of sugar molecule here, and then this giant complex protein. See that as the complexity goes up, if you wanted to, say hit this molecule right there, all right, you've got a million opportunities to collide with this molecule that are nowhere near there. So most collisions aren't going to be effective. The other aspect of the nature of the reactants is their state of matter. Gases are really spread out. So some people think, oh, they're so spread out, it's going to take longer to react. And that's actually not the case. Because gases have their molecules so spread out and they're moving pretty quick, what that does is it just exposes all the molecules to the other reactant. If all the molecules are easy to access, then it's going to lead to a really quick reaction. All right, gases also tend to be made up of small, simple, symmetrical molecules as well. So there's a couple good reasons why gases can react really quickly. Solids and liquids are tightly packed together, right, as we can see in here. That means it's going to be hard to get at all the molecules. That's going to slow the reaction down. Two liquids will typically react quicker than a reaction involving a solid, but they're still not going to react as fast as two gases because you have to take time for the molecule of the other reactant kind of jitter its way through and actually reach these liquid molecules. Whereas in a gas, that's not really an issue. Other note is just solutions do tend to react faster than solids and liquids, but slower than gases. That's a huge generalization, all right? But people always ask about how solutions fit in there, so I included that. You're going to watch some video clips that help show these things, a couple hydrogen balloons, all right, just hydrogen reacting with oxygen. Those are really simple molecules. You'll see those reactions are really fast. Got one of methane bubbles, which is just the reaction of CH4 with oxygen. You'll see that goes pretty quick. And then a reaction of potassium permanganate with glycerol. One of those is a solid, one's a liquid. The molecules are also more on the complex side. So you'll see that that reaction takes a while to get going. And once it does get going, it takes longer to finish the reaction than with gases. Okay, so just a couple videos to help illustrate those points. After those videos, you're going to start delving into a video on energy diagrams because this directly leads into those. The nature of the reactants determines how much energy those reactants store just by being themselves, right? So we know reactants go here on an energy diagram, all right? And we also know that there's a certain amount of potential energy that goes along with that position on the energy diagram, okay? So molecules store energy just by being themselves, all right? Just a couple reminders, we know reactants are here. We know that you end with products over here. One thing we could get off of this energy diagram is that these products are probably the more stable, simpler molecules because they have less energy. And less energy stored means you have a more stable substance. So in this case, we could predict these products are more stable substances than the reactants were because of that lower energy. Right, the energy diagram video got a little bit long. You can take a break halfway through or pause it. All right, take some notes or whatever. go for it. Right? But first, just enjoy the methane bubbles and other videos that I have for states of matter.